Hi, let's talk about the final results from Fermilab's Muon g-2 experiment. The Muon g-2 experiment at Fermilab just released a new measurement of the anomalous magnetic moment of the muon, or equivalently Muon g-2, sometimes written as g-2 with mu as a subscript. When they released their previous result in 2023, it disagreed with the standard model prediction by 5.1 sigma. And Muon g-2 is a place where many types of new physics could show up. So, the discrepancy between the measured value and the standard model prediction has been of great interest to particle physicists. The 2023 measurement showed a greater than 5 sigma deviation from the standard model prediction, and 5 sigma is a conventional threshold in particle physics for when a discovery might be declared. But there were some questions about the standard model prediction at the time, and no discovery was declared. Links and references to the old and new results are given in the description below. I'd recommend you watch the scientific seminar from Fermilab to get a fuller picture of the new result and context. Here, I'm just going to give a summary of the updated results. For loads of background information, you can check out the playlist Mini-Series on g-2 of the muon, available on this channel. Let's look at what was going on in 2023, when the previous measurement came out, versus the situation now. The 2023 experimental result was based on runs 1 through 3 of their experimental data, combined with the result obtained when the experiment was previously at Brookhaven National Laboratory. This new result uses data from runs 4 through 6 and is expected to be the final result of the experiment. You might think that the amount of data in the last 3 runs would be similar to that in the first 3, but actually the amount of data in runs 4 through 6 is about 2.6 times that in runs 1 through 3. Both results were expressed in terms of a quantity called A mu, which is just Muon g-2 over 2. Here's what the comparison of the 2023 experimental result to the standard model prediction looked like back in 2023. Here, the first term on both sides of the first equation is the experimental result from 2023. The second term is the standard model prediction as it stood at the time, subtracted off. The last line shows their difference. For each number, its associated uncertainty in the last few digits is given in parentheses at the end. You can see the difference is much larger than its uncertainty. In fact, the difference amounts to 5.1 times the uncertainty, or 5.1 sigma. Now, that experimental result is what is being updated by the Muon g-2 experiment at Fermilab. But an important point is that the standard model prediction was also recently updated. Both the old and new values for the standard model prediction were produced by a group called the Muon g-2 Theory Initiative. Their previous result was put out in 2020, and that is the number that was used in the comparison with experiment in 2023. They updated their calculations and put out a new prediction just last week. Here, I will give just a few slides about the update, but for more information, you can check out the video A Theory Update 2025 on Muon g-2, available on this channel. The main update in the standard model prediction came from a change in the way they evaluate a class of Feynman diagrams called hadronic vacuum polarization diagrams. A schematic of these diagrams is shown at right. They consist of diagrams where a collection of hadronic processes connects to 2 photons, shown in the diagram by wavy lines. Previously, the main contribution to these diagrams was computed using something called data-driven methods. For this updated prediction, the Muon g-2 Theory Initiative switched to a tool called Lattice QCD. Let's just briefly discuss the difference in a couple slides. Lattice QCD is a first principles computation from the laws of quantum chromodynamics. It is very computationally intensive, but has had huge improvements in recent years. Back in 2023, the lattice QCD results were not yet adequately developed for use in the main contribution to the hadronic vacuum polarization diagrams. But that has changed in the last couple of years. In data-driven methods, on the other hand, you don't try to compute the quantity you want from scratch. Instead, you relate it to other quantities that you can measure. Then you derive the quantity you actually want from those measurements. Here, they related the hadronic vacuum polarization diagrams that they wanted to the process E plus E minus goes to hadrons. However, back in 2020, when the previous prediction was produced, the different measurements of the cross-section for E plus E minus goes to hadrons showed tension with each other, and that tension has actually gotten worse in recent years. So the Muon g-2 theory initiative concluded that the data-driven results were not adequately reliable given the current experimental situation in E plus E minus goes to hadrons. It's important to note, however, that these two methods should have agreed. This discrepancy is yet to be understood. Okay, let's go back to the comparison between the measured and predicted values of Muon g-2 as they stood in 2023. With the recent theory update, the standard model prediction, shown in blue, and the difference between experiment and prediction, shown in green, change. So here is the 2023 experimental result compared to the new prediction. We can see that the prediction has moved up, much closer to the measured result from 2023. In fact, with the updated result, the discrepancy between the 2023 experimental result and the standard model prediction has been reduced to less than 1 sigma, so that's a pretty big change. Okay. In that context, let's look at the new measurement just out from Fermilab. Okay, without further ado, here's their result from runs 4 through 6. Let's compare that with their result from 2023. At a casual glance, it might look like their new result has a larger error bar, but note that they've added a significant digit to their result, so their error bar has in fact reduced. Also, we can see that the results disagree by less than either error bar. So their new result is more precise and has good agreement with their previous result. And it's good to remember that this was a blind analysis. That means that analysis decisions were made without the experimenters knowing how their decisions would affect the final result. In fact, the Muon g-2 experiment is famous for the lengths that they go to keep their analysis blind. If you'd like more information on blind analyses, check out the video, What's a Blind Analysis? But the point here is that their consistency really is as impressive as it looks. Okay, they then combine their result from runs 4 through 6 with their results from runs 1 through 3 and get this result, which isn't too different from what we just saw. And finally, they combine that with the previous result from when the experiment was located at Brookhaven National Laboratory to produce what is essentially a world average for A mu. So that's the result that is most useful to compare to prediction. So here's the difference between that final average and the 2025 standard model prediction. We can see that the measurement falls within the prediction's 1 sigma error bar. Okay, let's briefly discuss the results. So first, let's note that the combined result is insanely precise. This is a huge experimental achievement. Now, let's ask a question. The previous discrepancy between measurement and the standard model prediction was very exciting, as it was possibly a hint at new particles or forces. So, what about new physics? With the new experimental result and the new standard model prediction showing good agreement, it might appear that the long-standing disagreement between prediction and measurement has been resolved. But as we saw, the error bar on the standard model prediction is considerably larger than that on the experimental result. Additionally, there are still questions to answer regarding the discrepancy seen in the hadronic vacuum polarization diagrams. The disagreement between prediction and experiment won't be truly resolved until that is understood. So it's safe to say that Fermilab's experiment has thrown the question back into the theorist's corner. It should be noted that the Muon g-2 theory initiative has plans for extensive improvements in understanding their results and reducing their error bar. They are far from done. And the experimental story isn't over either. Another rather different Muon g-2 experiment is expected to start in 2028 at J-Park in Japan. When the theory issues are resolved, the result may be hints of new physics, or a powerful tool for constraining and ruling out new physics models. Either way, this is a huge accomplishment.